Stars in general are, as they go through their life, they are doing things, and that's kind of what we're going to focus on for today. What are they doing in those processes and different types of stars? So on your screen, you guys have some notes, and the reason why we're going to take paper notes today is because you have all the information on your PowerPoint, but it's not organized because this is a cycle. And it's really hard to do a cycle on a PowerPoint. It's slide, 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 slide. And so we are going to talk about the life cycle of a star, and we do want to organize our PowerPoint slides. And so both of these are PowerPoint slides that are on our note that you already have, okay? But we are going to organize them on paper today. And hopefully it'll make sense as far as like what slide means what type of star we're talking about. All right, I got something in mind. All right. Again, on paper today, try to make these boxes as big as you can for you to fit on your piece of paper. There are some arrows. I try to label them so that you kind of get an idea of where we're going to be, where we're going to go for today's lesson. I would encourage you to follow along with the note, just like anybody would. But on paper, I want you guys to write down the important things that we mentioned here. You do not have to write down everything that's on the slide. You have the slides. They're yours, okay? You don't have to write down everything. But on paper, I would encourage you to take some notes, encourage you to think about what's the most important thing I need to know about this. What's the most important thing I need to know about this box, about that box, okay? Also, before we get started, today we're going to talk about the life cycle of stars. This map I have here, this road map, is a very generic life cycle, okay? It is not the life cycle, okay? It's not saying that all stars are going to follow this path. Okay, this is just a generic life cycle, okay? This is a generic classification of what will happen, but most of these steps will happen with stars. And so that's what we want to talk about and focus on today. And I'll mention that throughout our notes today. All right, so today is pretty much going to be a note day. And then you guys summarize them at the end. And that's it. You get an A+ for taking notes. I mean, that's your assignment today, is to take some notes. And I'm going to grade you on taking notes today. Okay? All right, so let's go ahead and get started. So again, the first slide there basically just says, make your notes like this. Second slide basically says, this is generic roadmap of stars. And then we're going to start here at the birthplace of stars called the nebula cloud. So this is the top left box. And this is the very first box for the birthplace of stars. It's called a nebula cloud. Okay. You are going to see and hear the word nebula a couple of times today because, again, it is a cycle. Okay. We're going to come back to the nebula again and possibly again and again. Okay. So again, this is a cycle, okay, for the nebula. So a nebula cloud is essentially the nursery of stars. This is a cloud, literally, of dust, gas, especially hydrogen gas. Okay. And this is where the stars get the matter to become stars. Okay. Now, we do need to mention this real quick, especially where did that dust come from? If this is a first generation nebula, well, that matter and dust came from the Big Bang. So it's mainly going to be hydrogen and helium. Maybe a little bit of lithium there. If it is a second generation nebula, it's going to have stuff from the Big Bang and stuff from the previous star that used to be there. If it is a third generation, it's going to have stuff from the previous star, grandpa star, parent star, and then of course Big Bang itself as well. And so depending on what generation the nebula is in and where it got that stuff to make new stars. Okay? And again, you'll hear me say the word stuff a lot. It is dusty and things like that. I am going to go kind of quick on this because you have these notes. So if I go too quick, you pull up your laptop. Again, you don't have to write down everything. So nebula is just where clouds or where stars get their matter. And again, where it got that stuff from depends on what generation it is in. This is a picture of a very famous nebula. Might have seen this before or might even know the name. It's called the Pillars of Creation. And the creation part is talking about the stars, where it makes the stars. Okay. Now, I want you to get a sense of scale on this. How big is that cloud? Really big. Those are stars in there. So that cloud is really big. Okay, I mean, bigger than solar systems. I mean, it's huge. This is a huge nebular cloud where all that dust is. Okay. You can actually see this with a halfway decent telescope. It'll spend a couple $100. You can see this. This is something that people look for in the sky. It's big. You can see it with telescope. And again, this is a pretty famous one as well. So you see all these little dots in there. Those are the baby stars that are forming. Eventually, this nebula cloud will make a whole bunch of stars, and it might turn into a galaxy eventually. Right? This is going to be a cluster of stars all together in this one area. It might make 3 galaxies. Might be a galaxy there, a galaxy here, a galaxy there. We don't really know exactly what's going to happen to it. It's going to take a really long time to see what happens. And you got to remember, us humans, we've only been seeing this for a couple hundred years, if that long, maybe 100, 150 years. Remember, telescope technology hasn't gotten that great yet. Okay. So that is a famous nebula cloud where the stars come from, where stars are born. So gravity is going to bring all that stuff together, and it's going to create our next box. We go down one, and that is our protostar. You guys are in engineering, you guys know what a prototype is, I hope. Well, this is kind of the same idea. It's a protostar, the first step of the stars. Okay. So this is the beginning of a star. All stars have a beginning. Okay. A nebula cloud condenses due to gravity. Gravity brings all that dust and hydrogen together. And once you have enough mass, enough gravity, you can start to do nuclear fusion and have light, which is a star. Okay? If you don't have enough mass, enough gravity, you're just going to be a ball of hydrogen gas that's not really doing anything. Kind of like Jupiter, kind of like Saturn. Jupiter and Saturn probably could have turned into stars if there was enough stuff, if there was enough matter for them. They won't now, but if there was enough stuff, Jupiter and Saturn basically made the same ingredient. They could have become a star too, but they're not big enough to be a star. Jupiter and Saturn do not do nuclear reaction like our sun does. Okay. So again, that gravity forces nuclear reaction to start. That releases energy in every possible way, including light and heat energy. So that's your first baby star. From here, after this box, you're going to branch out into 3 other boxes, right? And it's pretty common sense. The 3 boxes you're going to form are small, medium, and big. It depends on how much stuff there is in the nebula cloud. How much stuff can gravity get together? Okay. If there's not a lot of stuff, you're going to form low mass stars. If there's a decent amount of stuff, you're going to form medium mass stars. If there's a lot of dust, you can form high mass stars. And so the next 3 boxes are going to be the types of stars that you make. I apologize for the color of that one. I probably should change that. It's kind of hard to see. I try to color code the picture. So the top box of that column of 3, if you guys have any questions, just make sure you guys ask, is our low mass star. What I really want you to know about low mass stars is A, they're low mass, but they only have enough mass to make the element helium. That is what a low mass star is. It only has enough mass to make helium. That's the top box of our 3 columns. Yes, ma'am. So the low mass star can only make helium itself. Okay, so that's 2 protons. Remember, stars are hydrogen, 1 proton. You have enough gravity, put 2 protons together, you make helium. All right, so that's really all that low mass stars do. Okay? Medium mass stars, when they're living their life, they are going to make element around carbon. 5, 6, 7, 8 protons. Okay? There is no like cutoff, like, oh, you make nitrogen, you're not a medium mass. It doesn't really matter. There's no cutoff. But around 6 to 8 protons can be put together with a medium mass star. Okay? And that's where our sun is. Our sun is a medium mass star. And then if you have a lot of matter, you can make a high mass star. High mass stars have a lot of gravity. You can put up to 26 protons together. And again, it doesn't mean it will make 26 protons, just somewhere in that ballpark, okay? Iron is a super stable element at 26 protons, and so stars kind of stop at that point. Even the biggest stars, that's kind of where they stop when they make iron, a super stable isotope. Okay. So, now, are there stars in between? Yes. Okay, there are some little medium and some big medium, okay? But these are basic 3 categories for stars. Are they small, are they medium, are they big? Okay. But most importantly, what do each star make? Okay? So you should have some information in that 3 columns. All right, we're going to make our first loop. We're going to make our first cycle. We're going to do our low mass stars. There's no notes you need to take. Okay? Our low mass star is going to circle back into the nebula cloud when it dies. Right? So you don't need to write this down. It's pretty common sense. Low mass star, when it runs out of energy, it is simply going to collapse and be done, and then it's going to recycle back into the nebula cloud. So you have a little arrow going from low mass back to your nebula. Okay, so when it dies, it's done. Remember, it can only make helium. It's not going to have a very interesting life. Sorry. I don't want to make fun of the star or anything, but, you know, it's just making helium. That's all it's doing. It's going to die off and get recycled into the nebula cloud. Now, that starts making the nebula cloud a second generation, right? So we're recycling material. The nebula cloud had less hydrogen now and a little bit more helium because of that low mass star. So you see how the nebula changes over time, depending on what's happening with the stars. Okay? So that's the first cycle, and it can just cycle back again and again, a new low mass dead, new low mass dead, new low mass, and just sit there and cycle back into the nebula nonstop. But again, eventually you're going to run out of hydrogen to make stars, eventually. Okay. All right, so low mass, not really a lot going on with those guys. All right, so let's take a look at what happens to medium and high mass stars. All right, so this is the box for medium. You do not need to write all this stuff down for medium mass. Just remember that medium makes up to carbon, oxygen, somewhere in that ballpark. But medium mass stars, they are the ones that are your typical everyday stars. They have their main sequence, what we call them, main life stars. There are different types of medium-sized stars. We talked about this before, you know, based on size and temperature and luminosity and brightness and age and temperature, whatever, all those different variables. Our sun is a medium mass star, but that's a kind of a small medium mass star. It's a G, it's a girl. Our sun is actually kind of small for stars. But that's actually not a bad thing. It means it's going to last a little bit longer. All right, so that's just the normal life of a medium mass star. So the next box for both the medium and the high mass star, so we're going to have two boxes on this slide, box and box, okay? As the medium and the high mass stars start to die off, as they start to run out of energy. They're not dead yet, but as they start to run out of energy, they are going to start fighting gravity. Because they're fighting gravity all the time. Gravity pulling on the stars, they're sending out energy outward and making a sphere. When they run out of energy, gravity's going to start to win. They expand, and the medium mass stars, the row in the middle, is going to turn into a red giant. The high mass stars, the row on the bottom, are going to turn into super red giant, bigger red giant. Okay? The same process for both of them. Okay? So as they run out of energy, they're going to expand to fight gravity. Okay? Now they're still living, they're still doing their thing. Medium mass stars are still making carbon. High mass stars are still making iron, even as they're super red giant. Okay, they're still doing their thing. Okay, but they're fighting gravity. At this point, they are starting to lose their energy at this point. Our sun is a medium mass. Our sun will turn into a red giant someday. It will take up Mercury and Venus. Scientists don't think it will take up Earth, but it'll get awfully darn close. Earth will be new planet number 1. Earth will also be tidally locked, which means one side will always face the sun, and Earth's not going to be a fun place to live. We don't really have to worry too much about that. We're talking billions of years into the future. Us humans, we need to worry more about the next 1,000 years. Seriously. And we're going to talk more about that for the rest of the year. Super red giants are going to expand even more than that. Obviously, they're going to make a really big giant red star. And they are going to be redder. They're going to be cooler. Okay, they're not going to be yellow and white color. They're going to be redder colored, which is a cooler color, less temperature than what they used to be. Okay. We got some questions over here. Okay. All right. So now we have the next two boxes after medium and high mass. We got giants and red giants, or super giants. Okay. Now, at this point, the stars are going to run out of energy, and really interesting things are going to start to happen. So, I think we're on medium. All right. So, the death of a medium mass star. After it turns into a red giant, most of the time, it will continue to expand to where it just simply dissipates its matter. Okay? Not necessarily going to explode. We'll talk about that in a second. But it's going to continue to expand. Eventually, it's just going to and let everything go. Okay? It's going to dissipate. And that dissipation is going to create a new nebula. So this is where we start getting into the cycle again. Okay? But this nebula is called a planetary nebula. So when a star basically just lets go of itself, okay, it's going to create a planetary nebula. This planetary nebula has the word planet in it. That's where planets and moons and asteroids and comets and meteors, all that stuff are going to come from. And future littler baby stars. Okay? So when that one star releases its matter into the environment, gravity can bring it all back together millions of years later and start to make a new star, new planets, new comets, new asteroids, new meteors. Okay, and then that star starts the cycle all over again. The reason why we know that our sun is a third generation star is based on the elements that are in our solar system. They took time to make. Okay? Those elements do not come from a first generation star or even a second generation star. Okay? So those elements that are in our solar system, not only on Earth, but the moon, Mars, okay? Those elements came from a previous nebula cloud, or previous planetary cloud nebula on there. So after the red giant, it dissipates, turns into a big cloud, and then gravity will bring all that stuff together to make a new star, new solar system. Okay? So if you want to put anything in that planetary nebula box, you put this right here. Makes a new solar system, new stars, so like that. So again, that new star can start off as protostar and start the cycle all over again. Now again, as you make new stars from old stars, they're going to get smaller and smaller and smaller, right? You're going to have less hydrogen, less hydrogen, less hydrogen. That also means that your solar systems are going to get bigger element, bigger element, bigger element, and less hydrogen, less smaller element. Okay? So, after that cycle happens a couple of times, eventually that last star you make will turn into a dwarf star. Okay? That last star you make after that cycling again and again and again, you're going to create a little itty bitty baby star. It doesn't have enough mass to do anything. And a dwarf star is kind of the end of the picture, the end of the cycle. So eventually, a lot of the stars in the universe will turn into dwarf stars. And again, that's that recycling. Less material, less material, less material, less material. Okay? There are different types of dwarf stars based on their color. We've got red and white and blue and brown. But lots of different types of dwarf stars on there. Now, luckily for us, there's not very many dwarf stars in the universe. So what does that tell us about the age of the universe? That there are not very many dwarf stars. It's a young universe. We still got a long time to go. Okay, if all the stars were dwarf stars, that would be a very old universe, right? And so there's not very many dwarf stars out there. We're relatively still a young universe. Scientists think we still got billions upon billions of years left to go. Okay, so we don't need to worry about that too much. But eventually our sun will either go into a dwarf star or something else might happen. Okay, so that is the death of a star there. That's the end. That's the end of the cycle. Okay. All right, we have another path we could take, and that is the bottom path with the high mass stars. So after the super red giant, okay, the other option is that gravity could win the battle. Instead of dissipating its matter, gravity could bring it all together, do pressure, 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 pressure. Make that star smaller, 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 this super giant star, making it smaller, 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 smaller. Now, let's say you got a 2-liter bottle. You put the cap on it, plastic, and you put it under a machine and you did pressure, 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 pressure on that bottle. What's going to happen to that bottle? Yeah, it's going to blow up on you, right? It's going to blow up right in your face. All right, so the same basic thing happens here. With that star, gravity wins. Put pressure, 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 pressure on the star, and eventually that pressure is going to backfire, it's going to rebound, and that's going to cause the star to explode. Okay? So again, gravity brings it all together, goes, nope, can't do this, and it could explode. And that is called a supernova. Now here's the cool thing though. During that supernova, you get the pressure, 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 pressure. That is also forcing more protons together. So remember, stars can make up the iron. Iron number 26. How do we get 30, 40, 50, 60, 70, 80 protons together? It's that shrinking. When that star shrinks, it can make really big elements, all the way up to uranium, number 92. Okay? 92 is the largest naturally occurring element that we have found in our universe so far. And it's not only on Earth, it's on other places too. Okay? Now again, you might discover element 93 somewhere. Get all the scientists to agree with you, and I'll change my PowerPoint slide, okay? But based on the data we found so far, element number 92 is the largest element out there. And again, that comes from that shrinking right before it explodes. Then, of course, the star explodes. So what happens then? All the stuff goes everywhere. And that creates a new nebula. Okay? And again, that's going to create a planetary nebula. That can create another star, new planets, new moons, etc. Okay? So you end up with a cycling again after the supernova. So the supernova, gravity can bring all that stuff back together, make a new baby star, make new planets, new Earth, blah, blah, blah. Okay. Right? So again, the gravity wins, it collapses that star, and it causes that star to blow up fighting that gravity. Or gravity wins and it does not blow up. If gravity wins and the star does not blow up, it can turn into a black hole. And again, this is the end of the cycle if it turns into a black hole. If it's supernova, you can make a new baby star, right? But if it turns into a black hole, end of the cycle, end of the life of the star. So a black hole is simply that. It is a collapsed star due to gravity. And it is quite small now, but still had the same mass, still had all the same stuff that it used to have as a super red giant. That's a big star that you collapsed in on itself, made it really small. That is going to be a ton of gravity. So much gravity that even light, photon, radiation cannot escape the gravity. And so it looks black because there's no radiation or no light escaping it. Okay. Now, this was all pretty theoretical up until a couple years ago. I think it was 2017. We had to get the first picture of a black hole. And it looked kind of what you think, a black hole. Now, again, I want to make this really clear. A black hole is a thing. It's not just a hole in the sky. It is a thing. It is a collapsed star. Okay? But that collapsed star, that amount of gravity, just you can't see anything coming from it anymore. Okay? Most scientists think that most black holes are about the size of a town. So imagine taking a massive star, even bigger than our sun that had a million Earths in it, and taking all that matter and putting it down the side of Florence, Kentucky. That's a lot of matter. That's a lot of gravity in one spot. Okay? So much that matter can't escape, or light. Okay, 1 second. Let me come closer. What's that? Well, they look big, but they're actually, the matter itself is actually pretty small, but the field they generate is really big. Like they're, if you fall off the field, well, you won't be able to. But fancy stuff. So that's a good question. So if you have a black hole, how do you see it? I don't have a picture. I can try to put one up. But. So imagine you had a bunch of stars on my board. You had a bunch of stars up here. But somewhere on that board, there was a hole. You know, so you have all these stars here, right? But there's a spot missing. You know, there's a spot of stars missing. That could be a black hole. Looking at it with a telescope, you're not really looking at a black hole. You're looking around the black hole. You're looking at what's surrounding it, what's behind it, so to speak. Okay. I should pull up the picture, but it's a pretty famous picture that they took just a couple years ago. But it has light around it, and then nothing in the middle of it, because the light can't escape it. So if you remember on Monday, I said that the sun, it makes energy inside the nucleus, or inside the core. That energy takes 10,000 years to escape the sun before it starts heading to Earth. At least 10,000. I think it was 10,000 and 170,000 years. It takes years for that energy to leave the sun to get out of that gravity. Well, a black hole, gravity too much. That energy can't leave forever, basically. Okay. So I'll tell you what. It won't take me very long. Let me pull up the pictures. Yep, wrong thing. Well, it's just like anything. It's still a thing. It's still acting like a little star. I tell you what, let me pull up both pictures here. It's kind of hard to do because there's things behind my back. You guys see the black holes at home? At home, you guys see it? Okay. All right. Now, the one on the right is a fictional picture, but kind of what it would look like. So you can see the light around it, but you can't see it yourself. So you know that there's something going on there, but you can't actually see what it is. This picture over here, the one on the left, that is a real picture of a black hole. And this black hole is in the center of our galaxy, the Milky Way galaxy. Scientists think that every galaxy has a black hole in the middle. And that is what is keeping the galaxy together. So instead of it being like a star keeping a planet together, the black hole is keeping all the stars together. Okay? And all the stars are orbiting the black hole, just like Earth is orbiting the star. 2007, they took the picture. Now, I will admit, this is a virtualized picture using data from 7 telescopes, and then they combine that data to make this one picture. So this is not one telescope, oh, there it is, you know. So you have to kind of take that with a little bit of grain of salt. We are getting better at this, and we are in the process, not me, but especially America and other countries, we are in the process of starting to send out telescopes to outer space that will take better pictures for us. But that is the black hole in the center of our Milky Way. And you can see the hole there, light around it. Last little thing about black hole that's kind of cool. Let's say you were to approach a black hole. Let's say it was on the ground. If you were to get close enough to fall into its gravitational well, the gravity on your feet would be different than the gravity on your head. It would pull stronger on your feet than it would on your head because your head's further away from it, right? It would pull so much differently that it would start to stretch your toes out, and then it would start to stretch out your feet, and then it would start to stretch out your ankle, then it would start to stretch out your leg, then it would start to stretch out your knee, your hip, your chest, and eventually your head will get stretched out due to the gravity. It's called spaghettification. And matter, as it approaches, it turns into a string of atoms. It turns into like a noodle of spaghetti, and it starts to thin out as it falls into the black hole. Now here's the messed up part. Because time slowed down around gravity, you'll see it happening to yourself. You'll see your feet doing that. So it's actually kind of a cool concept. Time basically stops at a black hole. Time and space don't work anymore. So you actually like literally see your body doing this. So it's kind of interesting, kind of crazy. You'll be dead, obviously. But let me make sure I heard it correctly. What was it? No, but we don't know what's possible. Now, there are a lot of movies, there are a lot of TV shows that talk about black holes and time travel and all that stuff, but time does not work in black holes anymore, the way we think of it. So, who knows what's possible around a black hole, especially if you fall into it or something like that. I will say that the movie Interstellar, I don't know if you guys have seen that one, that was a couple years ago. That's probably one of the best depictions of what a black hole would look like, and time dilution with black holes and planets. That's probably one of the best movies that does that part. Now, it got really crazy when he fell into it. That was really weird and messed up. But who knows? we don't know what happened when you fall into a black hole. We've never even gotten close to a black hole, so I don't think we ever will. But. Yeah. All right, that's it for me. You guys at home? That's it for me. There are some additional resources if you guys want to learn a little bit more about it. Again, that life cycle is super generic. Lots of things can happen to stars. Those are just the basic stuff. Your assignment for today is to upload a picture of your note and just do a quick summary. That's it. Okay? And again, you should easily get an A+ on that. Activity A, B, and C. This week's activity. Technically due today at midnight, so try to finish that up for me. We had to put in our failure report. Not a lot of you, but there are some of you. If your grades are not super hot, try to spend an hour or two this weekend getting some work turned in, okay? I know that's not fun, but trust me, your future self will thank you for getting caught up a little bit at a time instead of having to spend 2 weeks or 3 weeks or summer school getting caught up, okay? So again, spend an hour or two, just try to get caught up. I would knock out the quickest thing first, and then work on the big stuff later. So if you got a 5-page essay, and you got a 10-minute assignment, do a 10-minute assignment first, then do the essay. All right, that's it for me. We still got a couple of minutes, so just kind of hang out, chill. Next week, we'll talk about nuclear reaction next week. And then we do have a quiz on Friday scheduled right now. All right, let me turn all this off.